So the next chapter is scripted by two people, De Broglie and Schrodinger. So today we will start with what De Broglie did, and I will give another assignment at the end of this week, which will kind of give you some hands-on experience with one problem, especially which Heisenberg's method is still the what to say the method that we use to quantize, and that is the harmonic oscillator. So, and another announcement is that the midterm exams are being graded. It's almost done. One of the TAs has an experiment running, so he's a little caught up with that. But positively, before Wednesday's class, we will return the exams. And I'll put up the solutions so you can go through them and ask any questions that you may have. All right. Okay. So we discussed how Bohr's correspondence principle led to Heisenberg's matrix mechanics. And in matrix mechanics, you consider the Fourier series of any classical variable, and you basically write the equivalent of that using quantum theoretic expressions. And Heisenberg made the discovery that this leads to these Fourier components not being simple numbers, but they have to satisfy matrix multiplication rules. So they are actually matrix elements. And this was the status as of 1925. 1925, Heisenberg's what was then called matrix mechanics. It was a huge step forward in kind of tying the classical and the quantum regimes together, not via a vaguely stated thing called the correspondence principle, but by on more solid ground. But mathematically, it was a nightmare because you had to now deal with infinite dimensional matrices, and matrices themselves were very new to physicists. A few mathematical physicists had, like Hamilton and others, had worked with, uh, you know, uh, matrices, but largely the physics community was unaware of matrices. So this was where people like Max Born and others who were in the spectroscopy area where they started applying some of these techniques. They recognized that matrices were and they took off from Heisenberg's work and matrix mechanics as a solid they laid a solid foundation for matrix mechanics in another paper, which was published a few months after Heisenberg's paper, again in 1925, where Max Born, Jordan, and Heisenberg worked out several results, including the harmonic oscillator and various things. But we are not interested in all that because from a historical point of view, what Heisenberg did was the first big step. And after that, it was a matter of simple deductions by Born and others. But there are severe shortcomings with matrix mechanics. Okay, shortcomings of matrix mechanics. What are those? One, the theory is rooted in periodic systems. If you remember the entire Bohr's correspondence principle, the Bohr quantization condition, and what Heisenberg did in terms of a Fourier series, all of these are valid only for periodic systems. So which means a simple system like an electron in free space was intractable using matrix mechanics. People were still applying classical physics to that, but there were some problems we will come to see in a minute. Why classical physics doesn't completely describe electrons moving in free space. And secondly, the second difficulty was, of course, mathematical difficulty, which was people who were familiar with matrices knew that matrices were a structure which went hand in hand with another structure called vectors. For example, if you have a matrix, for example, if you have a system of linear equations or differential equations that you want to solve using matrices, using the methods of matrices, then this matrix of the coefficients of the linear equation is usually acting on a vector which is the vector of independent variables that you want to solve, or the different variables that you want to solve for. So this is the method. So a matrix has corresponding to it some sort of a vector on which this matrix acts. Now, there was no mention of any vectors in Heisenberg's language. So these vectors are somehow missing. So what are these vectors? So that was a question which was mathematically, we did not have any explanation. And we will see later that this question of what happens to the vectors in matrix mechanics is essentially, the question can be rephrased as, how do you define the state of a quantum system? Okay. So this question of what is the state of a quantum system, vectors in matrix mechanics were missing, implies state of a quantum system was not described in matrix mechanics. And of course, the third question is, you have PQ minus QP, and we put hats on these to signify that these are h by 2 pi I. This was Heisenberg's, it was not called uncertainty principle, by the way, at that point of time. It was called the Heisenberg commutation relation. And what does this physically mean? Physical meaning of this was also not very clear. It was derived as a consequence of the Bohr quantum condition, but that's it.
Excuse me,
A
sir.
very different,
Uh,
yeah.
so can you please explain the second point why vectors were missing in matrix mechanics?
Oh, because the entire thing revolved around square matrices, square infinite dimensional matrices. Now, whenever you have matrices, right? These matrices in general, uh, in mathematical methods and anywhere where you have matrices, matrices have eigenvalue equations, right? For example, you take the matrix that you construct for, say, position or momentum, or say the energy of a harmonic oscillator or any hydrogen atom, all these problems. There are eigenvalue equations. Now, you can apply this eigenvalue equation and get the eigenvalues for, say, the hydrogen atom. Heisenberg and others did this. But what are these vectors? They had no clue. They took they took the matrix of the uh, Hamiltonian that they could construct using Heisenberg's prescription. And they could also, this Hamiltonian was not necessarily always diagonal. So they had to diagonalize it to get the eigenvalues. But to diagonalize it, you need the eigenvectors, right? Now, what is the physical meaning of these eigenvectors? What are these eigenvectors? They had no clue. That's what I mean by the vector, the description of vectors, or equivalently the description of the state of a system. This equivalence between the vector being the state of the system is of course later. I'm only stating this in both these terms, but at that point of time in history, what do these eigenvectors mean at all? That was what they were not clear about. Is that
So,
clear?
Okay.
at that time, there is a concept of vector space, and there should be a vector space for this Hamiltonian, and why there is a difficulty to
Exactly.
find this eigenvectors.
No, they had, of course, they computed eigenvectors, they computed the eigenvalues. But what is the physical meaning of these eigenvectors? That was not clear to them. They constructed, of course, to diagonalize a matrix, they need eigenvectors. They mathematically they went about it, but what is the physical meaning of these vectors? They did not relate it to any sort of a state of the quantum system. In the sense, they did not say, oh, this describes the state of this electron in the nth orbit or anything like that. So it was not clear to them as to what this represented. The connection was made by Schrödinger. So we will see how Schrödinger bridged all these gaps. Okay. So this was the state of affairs. It was not very pretty. And mathematically, of course, it was a nightmare. Even the simplest problem called the hydrogen atom was extremely difficult using matrix mechanics. In fact, Bohr's correspondence approach was probably more attractive because there you had classical mechanics coming to your rescue and you applied the quantum condition only in certain places and that's it. But the answer to all these questions came from a different direction. Louis de Broglie, a French scientist, was interested in a completely different problem. So this problem dates back to a very long time. In fact, Newton was the one who first conceived such a problem. So we all know very well that you have certain laws in geometrical optics. And what are geometric optics laws? You have laws of reflection, laws of refraction, and the law of refraction especially is called Snell's law. And what does Snell's law say? That if you have a medium which has a refractive index n1, or if you have two media with an interface between them, and this is the normal, and you have a ray of light incident in one medium at an angle theta, then it bends. This is an experimentally observed fact, and this is an empirical formula that if you have n1 and m2 and 2, then n1 sine theta 1 will be equal to n2 sine theta 2, which means n2 by n1 is sine theta 1 by sine theta 2. This is Snell's law, which all of you are quite familiar with. And this was very well known back in the 1700s and 1600s. And Young and others, Fraunhofer, Fresnel, Young and others did a lot of studies on the wave properties of light in analogy with the waves of, in a water tank, which all of you have probably encountered in school sort of descriptions of the Young's double slit experiment. And Snell's law, laws of reflection, etc. could all be reconstructed from the wave theory of light using what is called the Huygens principle. Okay, that if you have a wave, at every point of the wave you have secondary wavelets which keep coming out. So every point on the wave acts like a point source which emits spherical wave fronts, and looking at the interference of these and directions, etc., they could reconstruct results from classical optics and under certain approximations. The approximations being that the wavelength at which wave optics and classical optics kind of merge is very, very, very short wavelengths. Okay. Now, Newton had a very interesting observation that he made. So he said, consider a point particle. He was not interested. He was not really talking about waves or light. He was talking about consider a point particle of mass m. Okay. And it is moving in a medium. Let us say you have two media. You have a medium with potential V1 and you have a medium with potential V2. I just drew it like this to kind of look similar to that diagram up there. And let us say you have this point particle which is moving. Okay. uh, yeah, with a velocity v1, and assume that this potential v is actually constant everywhere. There is just a difference between these two media, but otherwise the potential is not really dependent in space or anything. And this particle is moving with a velocity v1, and it enters this other medium. Okay, what happens at that point? Okay, let us say, let's reconstruct exactly the same scenario, and it's moving uniformly because there is no potential difference or something. So this, the potential doesn't change, so there is no gradient, meaning there is no force. So whatever direction this particle is moving in, it will now move uniformly. And my diagram here looks absolutely non-uniform, so let us say it comes like this with a velocity v, with a velocity v1 bar, okay, in this particular direction. So obviously you can resolve it into vectors. Okay, so this one here will be, this is theta. So the vertical component will be v1 cos theta. The horizontal component will be v1 sin theta, right? And theta 1. This is v1x, this is v1y, or the other way around. This is, let us say this is the y direction, this is the x direction. Now, conservation of energy says the following, or just the energy, kinetic energy of this particle. Let us say this particle has total energy E. Then the kinetic energy is half mv1 squared equal to E minus V, right? Now, at this interface, okay, at this interface, there is a change in the potential along the y direction, which means classically, it means that there is, and this potential kind of changes instantaneously, or rather within a zero distance. So it is like an infinite force, but which acts momentarily. So it's like an impulsive force that acts on the particle. Okay. Now, because this force acts only in the normal direction to this interface, the horizontal component of velocity should still remain, horizontal component of momentum should remain conserved. And since it's the same particle that we are talking about, let us say in the second medium, let us say the particle is moving now with a speed v2. The total energy still remains E, and the uh, the particle has energy E minus v2, and the horizontal component of momentum remains conserved, which means v1 sine theta 1. Remember that this is the horizontal component of momentum, is v2 sine theta 2. In other words, v1 by v2 is sine theta 1 by sine theta 2. Sorry, v v2 by v1, v2 by v1 is sine theta 1 by sine theta 2. Okay, which is equal to, and from these equations here you can construct a formula for this, and this will be square root of E minus v2 divided by square root of E minus v1. Okay, and according to Snell's law, this will be n2 by n1. So Newton made this connection that geometrical optics and particle propagation have some similarity. That is, the Snell's law kind of holds in a different form. It's not the ratio of refractive indices, but the ratio of velocities. And he even said that the refractive index of a medium, you can construct a refractive index of a medium for particle motion, and that would be related to square root of E minus V. That is, if you think of light as a stream of particles, if they had a certain energy, and you think of this medium as having a certain potential energy, then the refractive index of that medium will be related to the square root of E minus V. This was the sort of loose connection that Newton tried to make. And this was the story well before de Broglie. But this was the idea that de Broglie was interested in, to see if there was any way in which the particle motion can be described using waves. Okay, sort of a wave equation. Now, why was this even interesting? Because around the same time as Bohr's and Heisenberg's work was happening, there were two scientists, Davison and Germer, who quite serendipitously discovered electron diffraction. They did not even know that they discovered electron diffraction. They had a stream of electrons impinging on a metal target, and the metal target, so the way I think it was a nickel target or something, which they had, yeah, they wanted to just see what happens when electrons impinge on this target. I don't know the exact history, but there was a fire accident once in their lab. One night there was a fire accident, and the the metal sort of, it melted off. I think one of these metal targets melted because in the fire accident, and it recrystallized. And once it recrystallized and they did the same experiment with the target, they found that there was an emerge from metal target, which they could not explain. After this fire accident, this recrystallization kind of took it into a slightly different phase. Let us say it was in an FCC phase or something, and then it went into some other phase of its some stable crystalline phase. They saw that this pattern changed, and they kind of had this feeling that the experimental setup was exactly the same. There were no X-rays anywhere. This was just an electron beam impinging on the target. And why did the pattern change for the same element? Then they figured out that this must be due to uh, a change in the crystalline phase. So what we are seeing here is similar to that of X-ray diffraction. And then they, of course, did a whole bunch of controlled systematic experiments and confirmed that electrons underwent diffraction. Now, what is the underlying principle of diffraction? Underlying principle of diffraction, a diffraction pattern like that of X-ray diffraction is interference, right? For example, you all did X-ray diffraction this semester. So the simplest picture, the Bragg picture of diffraction is basically you take two planes, crystal planes, think of them as simple mirrors, sort of partially silvered mirrors or something, which don't completely reflect, but at each interface there is a reflection, and the path length that this second ray travels between the planes becomes the basis. So if this is d and this angle is theta, 2d sine theta, if that is equal to n lambda, then along those directions of theta, you find constructive interference, because n lambda means it's an integral multiple of wavelengths, which means that the path difference between the phase difference between the waves between this wave or this ray 1 and ray 2, the phase difference between these two waves will be integral multiples of 2 pi, which means they will be in phase with each other and therefore constructive interference. So in other words, diffraction requires interference, which is a quintessential wave phenomenon. Diffraction implies interference, okay, which in turn implies principle of superposition, okay, which implies not just any waves, but linear waves. What do we mean by linear waves? Waves that are solutions of a linear wave equation. Okay, that is, they can be described by solutions of a linear wave equation. Let me pause here for a minute and try to explain. There are two things that I mentioned here. Diffraction means interference, and interference means waves. That's a qualitative way of seeing it. Principle of superposition is very important for interference because when two waves pass through each other, okay, the they superpose, right? They superpose, and at points where they have complete phase matching, they superpose constructively, and at points where they seem to have completely out of 180-degree out of phase with each other, they seem to destroy each other, right? So this principle of superposition holds. So if you, for example, if you have two waves coming in both directions, you will have a sort of pattern where the wave has a large amplitude in certain regions of space and has a very small amplitude in certain regions of space over a certain period of time. And if these are, say, finite extent waves, that is, these are like wave packets which don't extend infinitely in space and time, then these kind of just pass through each other without doing anything to them other than superposing for that brief period. So the propagation of waves in any such linear medium, say like free space or many other dielectric media, etc., was described in electromagnetic theory using linear wave equation. And we already saw linear wave equation. We all know that very well. So the linear wave equation is, you always have some, I'm also introducing gradually, I'm slipping in notation which is similar to what uh, you will ultimately see in quantum mechanics. But let us say you have some quantity. It could be an electric field, it could be magnetic field, it can be the displacement of a string that is fixed at two ends, whatever it is. That parameter, that quantity psi, satisfies a wave equation which looks like this, where x is the direction of propagation, u is what is called the phase velocity, and you all know these terms, so I'm not. This is the equation of waves, the linear, it's called the linear wave equation. Okay, and this is in one dimension, in 1D. In 3D, this just becomes grad squared psi, okay, grad squared psi minus 1 by u squared d squared psi by dt squared equal to 0. This is in 3 dimensions. Okay, so Davison and Germer's experiments meant that electrons should be described using waves in some sense. So de Broglie latched on to this idea and he wanted to proceed and see how far he could go. And how do you then proceed uh, based on this idea? It turned out that Einstein, from a completely different starting point, Einstein had uh, worked out a few relations. So in special relativity, which we are going to discuss in a certain amount of detail in a few lectures, in special relativity, if energy of the photon is E, its momentum is given by E by C. Okay. And later on, a few years, in fact, uh, a few years after Einstein proposed the relativity, the theory of special relativity, he applied Planck's quantization, where E equal to h nu for electromagnetic radiation. And if you now look at these two formula, formulae, you see that an electron, a photon with energy h nu will have a momentum h nu by c, which is basically h by lambda, because c nu equal to lambda in uh, this is the relation between wavelength and, sorry, nu lambda equal to c. What am I writing? Looks like you guys are not paying attention. Nu lambda equal to c is the relation between wavelength and frequency, and using this we can write the momentum as 1 by lambda. Now this, de Broglie saw a very interesting thing here. Frequency and wavelength are wave properties. Energy and momentum are particle properties. So what Einstein did here, the energy of a harmonic oscillator being related to its frequency and the momentum being related to inverse wavelength, both through the same constant, which is the Planck's constant. To de Broglie, this was a very interesting thing because it was tying, it was marrying two very different ideas. Frequency and wavelength were wave properties. Energy and momentum were quintessential particle properties. So this he used as a clue and said, now that light is very well established as a, uh, diffraction, meaning we know that light has wave behavior. Can I now extend that formalism? Hello, can you hear me?
Yes, sir, we can hear you.
Hello. Yeah. Can I now extend this formalism to all massive particles? Light was a massless particle, but let us say I have a massive particle like the Newton experiment. How do I go about describing it?
Excuse me, sir.
Yeah.
Sir, you said that, sir, in special relativity, P equal to E by C, is this applicable to both
Oops,
light
something.
as well as massive particles?
P equal to E by C. No, that's not
Yes.
applicable to. Something happened. Something happened. Just hold on for a second.
Yes, sir.
Yeah. No, no, the notes that I was just writing, somehow it disappeared. That's okay. Fine. We'll reconstruct it. Lecture 22, for some reason, it disappeared. That's okay. Let me restart. Yeah, sorry. You were asking a question?
Sir, in special relativity, momentum is equal to E by C. Is this applicable to light or massive particles or both?
Oh, that is only applicable to light. For massive particles, we have the other relation, which is E squared equal to P squared C squared plus M squared C power 4. When M is 0, E becomes P by C. E by C becomes P. This is only for
Okay.
massless particles in relativity, and we will look at all this in a few lectures. But since you are familiar with E equal to E by C equal to P in relativity, I thought I'll just use that fact. I won't be using any more relativity, so don't worry. Uh, that was the interesting thing here is that the relation between two wave properties like frequency and wavelength being related to two very classical mechanical particle properties like energy and momentum. These were this was the interesting connection. So what de Broglie did was extend the wave description, or at least he attempted to extend the wave description to particle dynamics. So how did he go about doing this? You have the wave equation. Let's take in one dimension, d squared by, or let's take in 3 dimensions. Why? I mean, it's not mathematically any more difficult or less difficult. Let us Just you have del squared u, sorry, this minus 1 by, this is the wave equation, and he wants to construct a particle equation for this. Now, what is the goal? A similar equation for particles. Now, if that has to describe particle dynamics, it should not have this u is a phase velocity, which is a wave property. So he wants to describe, he wants to remove this u in terms of particle properties. So now u, we know, is, he then applied for massive particles. De Broglie applied the principle that Einstein, the relation that Einstein worked out for light. What he said was, instead of c being the speed of light, I'm now going to say that for any finite velocity u, I'm going to define something called phase velocity, which is defined as this E by P. He said, I'm going to now define a phase velocity as E by P, and this P is the momentum, and this is the total energy, and this is going to be 2m E minus V, where V is the potential energy. Why? Because half mu squared will be, okay, half mu squared will be E minus V. Sorry, what am I writing? That's not correct. What I mean is P squared by 2m. If P is the momentum, if P is the momentum, P squared by 2m is E minus V. Therefore, P is square root of 2m times E minus V. This we know. And if you now define the ratio E by P as E by square root of 2m E minus V, this is the definition of phase velocity that de Broglie extended to all other particles. Okay. Now, then he said, like for light, I'm going to now define E by H. Okay. E by H, because E has units of energy and H is Planck's constant. I'm going to define E by H as the frequency of the particle. Basically, frequency is related to energy. So again, he's using the same uh, technique that of Einstein, and he's defining. I'm going to now define the frequency as E by H for a particle. Okay. So what happens to the phase velocity now? The phase velocity becomes, you write E by H, and then you write by H here also. So you take H inside, what you now get is nu divided by square root of 2m by H, okay, times nu minus V of xyz, which is the potential, divided by H. So the phase velocity is now nu divided by square root of, he called this 2m by H as 2 mu, okay, some sort of m by H is like a ratio of mass of the particle to the Planck's constant. So it's 2 mu, nu minus, and this function here, he denoted it by D, which is called the de Broglie function, which is nothing but the potential energy divided by H. Okay. Now,
So,
yeah.
why was mass replaced by mu?
Oh, that's just he just reparameterized the equation in terms of, he consistently divided everything by H, right? So this comes out as mu, 2m by H, or m by H is what he calls mu. H is a
Okay.
fundamental constant, so it is sort of a different quantity which is related to the mass. That's all.
Okay, sir.
Okay. So now the goal is express a linear wave equation entirely in particle properties, right? So if you have u This is the phase velocity. Now this has square root of 2 mu nu minus d of xyz. This is the relation you first have. So first, let us start with the linear wave equation. We know that the linear wave equation is d squared minus, gradient squared psi minus 1 by u squared, okay, is 0. How do you typically solve this equation? You solve it using variable separable method. So you first take this del squared psi by del t squared, and you say that this is equal to some minus omega squared psi, right? I mean, you all know this part. Now omega is 2 pi nu usually. So this is exactly what de Broglie did. He said, okay, let us take del squared psi by del t squared equal to minus 2 pi nu squared of psi, and then plug it into the original equation del squared psi minus. So this is how you solve for, I mean, solving this equation for the eigen solutions for the normal modes. Okay, this is precisely what we did when I gave you the problem for, or before we discussed Planck's black body radiation problem. We discussed this problem about a string being held at both ends and then a electromagnetic field inside a cavity. And this is the wave equation, and this is how we solved for it. And you now substitute this back into this, you get del squared psi minus, or rather plus, because this is minus of this 2 pi nu by u whole squared psi equal to 0. In general, this equation is called what? Does somebody know the name of this equation? It's called the Helmholtz equation, right? Now, so this is the wave equation. So he starts from the wave equation, and this is the harmonic oscillator equation, which defines these frequencies. And you substitute that into the wave equation, and you get what's called the Helmholtz equation. Now, here is where he started applying his relations, the relations that he worked out here, to this equation. He said, okay, I have del squared psi plus 2 pi, that is 4 pi squared nu squared divided by u squared. And I know u is this. I write down u. So u is going to be nu squared divided by 2m nu minus d. D is a function of x, y, z. Okay, 2 mu rather. 2 mu times d times psi equal to 0. So del squared psi plus 8 pi squared mu, okay, times mu minus d of xyz equal to 0 times psi equal to 0. Now this equation is describing this d here is the potential energy that the particle is seeing. This mu here is related to the mass of the particle. So in some sense, we are inching towards a description of the dynamics of particles using a wave equation. But there is one problem with this equation, which is there is still a nu here, which is a wave property. So we don't want a nu hanging around. So what de Broglie did was he again used the wave equation. So he said, okay, I'll write this as 2 pi nu minus d of xy z times psi equal to 0. And instead of 2 pi, I'll use this again.
Excuse me, sir.
Yeah.
Shouldn't it be 2 pi d instead of just d?
Oh, 2 pi. Yeah. sorry, correct. It should be 2 pi d. And here I said I'm going to write it as 2 pi nu times psi, right? Now from the original equation or from this equation, I can write 2 pi nu, okay? 2 pi nu times psi from this equation as minus del squared by 4 pi mu plus 2 pi d of xyz, of course, acting on psi, okay? By just rearranging this equation. I just rearrange this equation. This is equal to 0. So I just take this del square to the other side divided by 4 pi mu, and then take the 2 pi d to the other side, and I get an expression for 2 pi nu psi. So I just look at this equation here, and instead of 2 pi nu psi, I apply this. And what do I get? Del squared psi by del t squared. Okay. Del squared psi by del t squared equal to del squared by 4 pi mu, okay, plus 2 pi, sorry, minus 2 pi d of xyz acting on psi, right? This is, so what I'm doing here is this 2 pi nu psi I'm replacing by this, but there is an additional 2 pi nu psi here. So I'm going to have, I absorbed the minus sign already. So I'm going to have another 2 pi nu psi here sitting here. So I'm now going to apply this again. So I had del squared psi by del t squared equal to minus of del squared by 4 pi mu minus 2 pi d of xyz whole squared acting on psi. Therefore, by rearranging this equation, what I get is the following: minus del squared by 4 pi mu plus 2 pi d of xyz whole squared psi plus del squared psi by del t squared equal to 0. Now this equation has no nu and is written in terms of mu and d, which are purely particle properties. D is related to the potential energy and mu is related to the mass. And de Broglie said that such an equation should be now taken as the equation for describing the particle motion using a wave equation. Okay, this is the wave equation describing particle motion. This is what de Broglie conjectured. Now, let us just look at this equation once for a few seconds, and you will see that this is a fourth order partial differential equation, which is usually very uh, difficult to solve, but still it's a step forward in terms of mathematical difficulty compared to the infinite dimensional matrices that Heisenberg had proposed.
Excuse me, sir.
Because hello,
Excuse me, sir.
yeah.
Sir, like in that step, we interchange the sign of del square upon 4 mu to minus del square. Like, would
Doesn't
that
matter because it's a square. Doesn't matter, right? It's a square. That's why. This is the equation. You can work out the maths. It's pretty straightforward. You get the same equation. All I'm saying is that this is a fourth order differential equation and fourth order partial differential equation, which is difficult to solve, but still much less difficult compared to Heisenberg's equation. But there is one problem with this, which is that when you note, you want nu to correspond to the energy of the particle, right? We want nu to correspond to the energy of the particle. And how do you solve this equation? If you consider this the wave equation, you solve this by first saying d squared by dt squared, which is the time part of this equation, should be equal to minus 2 pi nu squared e, oh sorry, psi. So to solve for the eigen solutions of this wave equation, we have to start from this point, which defines the energy of the particle via this frequency nu. But since only nu squared matters, both plus nu and minus nu will be part of this, meaning this equation is not describing particles moving with energy E, but it's describing particles moving with energy E and minus E at the same time. So immediately de Broglie discovered that, oh, obviously this is degenerate in the sense that if you have a certain energy E, both nu and minus nu solutions describe the same particle with energy E. So in that sense, it's degenerate, but this can be easily resolved. Instead of taking del squared psi by del t squared equal to minus 2 pi nu psi, let us take the square root of it and instead put del psi by del t equal to minus I 2 pi nu psi. This is the square root of this equation. It's very easy to see. You just apply del by del t again and use the same equation and you will get d squared psi by dt squared equal to minus 2 pi nu squared psi. So instead of using this squared where nu squared appeared, which caused a degeneracy in the energy because both positive energy and negative energy particles were being described, but classical mechanically, we don't have this possibility. So he wants to describe now. Oh, by the way, de Broglie was not attempting a quantum description in terms of waves. What de Broglie was doing was writing a classical wave equation for classical particle dynamics. That point
Excuse me, sir.
one should remember. Yeah.
Sir, how did we bring in the I in over here?
Meaning?
So the first equation is minus 2 pi nu squared psi, and then the
Oh,
second equation is
uh-huh. Uh-huh. Oh, if you don't have if you don't have I, you will get you don't get oscillatory solutions. You will get infinite blowing up solutions, right?
yes sir, got it.
That is the reason. Because after all, we want the nu, because we want after all the nu to correspond to the energy, which is a real quantity. So nu has to be real for energy to be real, which means you need the I so that the solution of the wave equation is not some exponentially blowing up solution, but an oscillatory solution. That's the reason.
Yes sir, got it.
Yeah. So to now you do the same thing again. So you say 2 pi nu psi from this equation here. From this equation, you have 2 pi nu psi equal to minus del squared by 4 pi mu plus 2 pi d acting on psi from the rearrangement. And we know 2 pi nu psi is I del psi by del t. Okay, I del psi by del t. So we now write down the wave equation, or this is called the de Broglie wave equation for particle dynamics, equal to minus del squared by 4 pi mu plus 2 pi d. Now, if I just rearrange it, so this is the de Broglie wave equation, and I want to classical wave equation for particle dynamics. Okay. Now, if you know we already know that mu is m by h. V by h is d. So if you just write these in terms of these quantities, what you get is IH del psi by del t. And you also note that 2 pi h by 2 pi is h bar. Okay. Then you get minus IH bar del psi by del t will be minus del squared by 2m plus 2 pi, sorry, not, there won't be a 2 pi, plus V acting on psi. Those of you who are familiar with Schrodinger's equation will immediately recognize that de Broglie basically derived this. But we are still not calling it Schrodinger's equation, and that you have to wait for one more class to declare victory. We are not yet there yet at Schrodinger's equation. But this looks deceptively similar. And how does de Broglie plan to apply this? One of the first problems that he applied, which had no description, which had absolutely no description in terms of Heisenberg's language, was a simple free particle in a region of space called the particle in a box. Before de Broglie, nobody had looked at this simple problem of a free particle in a box, which had no description in, it's not a periodic system. There is nothing, there is nothing that you can do in Heisenberg's language. But in de Broglie's language, this could be solved very easily. So what de Broglie did was he took this equation. This is now, we are going to call this the de Broglie wave equation. And it's a classical complex wave equation. Why complex wave equation? Because you have this I here. It's a complex equation. The psi, we still don't know what the psi is. De Broglie did an interpretation and he attained some success, achieved some success using that interpretation, but there were a lot of problems. So let us first look at the successes. Okay. This equation is a second order partial differential equation, which is derived from the wave equation. So basically this is the second order partial differential wave equation applied to particle dynamics, which is a very, very impressive result. And he now applied it to a problem which had no description in Heisenberg's case, which was a simple free particle in a box. And when you have a box, a rigid box, the potential energy at the boundaries, he took it to be infinite. Okay. And he thus applied this. So the potential energy is infinite outside this box. Let us say the box extends from say 0 to L. The particle inside is free. So there is no potential energy. V is 0 here and V is infinite at and outside the boundaries of this box. So inside you have del squared psi by del x squared. It's one dimension. Okay. So let us now write down the de Broglie equation for this particle. So it's del squared psi by del x squared plus 4 pi mu I. So this d term is 0 because potential is 0. 2 pi, I just take this 4 pi mu I to the other side and I rearrange it. Okay. Psi, d psi by dt equal to 0. Now, how do you go about solving it? Exactly like what we would do instead of this. So instead of del psi by del t, you are now going to take this. Okay, and you substitute this here. So you get del squared psi by del x squared plus 8 pi squared mu nu psi equal to 0. Okay, or let me be a little careful in the notation to solve for the eigen solutions, which we will represent by phi. Okay, these are eigensolutions. This is the general wave equation, and the general solution for a wave equation of this sort, which is a linear equation, is a superposition of the eigensolutions. So to know the eigensolutions, we impose this restriction. So the eigensolutions satisfy this equation. Any general wave, which is a superposition of several eigensolutions, need not satisfy that equation. Okay, so this equation defines the eigensolution equation. And you then plug in this and you get the spatial equation that is satisfied by the eigensolutions. And it's a trivial exercise. It's a trivial exercise. This equation is of the form del squared phi by del x squared plus k squared phi equal to 0. And we know that the solutions to this equation are of the form I sine kx plus b cos kx. But we also have phi equal to 0 at x equal to 0 and phi equal to 0 at x equal to L. Why? Because the potential is infinite and the particle has a finite energy, which means this phi has to now go to 0 at those ends. And using that boundary condition, he got a discrete set of eigen solutions given by kn equal to n pi by L. And b becomes 0. Therefore, phi n of x is some coefficient an sine knx. So there are only a discretely countably infinite set of solutions, and any general psi of x is now a summation over all n with some coefficient an sine n pi x by L. So a general solution. Why does this follow? Because this is a linear wave equation. This is a linear wave equation. Linearity is very important so that you can compute the eigensolutions and then take a superposition to form the general solution. Now, this is already very, very impressive. Now he wanted to quantize it. Okay. Now he wants to quantize it. Now, what do we mean by quantizing it? We know that it is one particle inside a box, but we have described it using some sort of a wave field given by the psi. So how do you relate the particle nature to the wave nature? So de Broglie called this quantization. This wave needs to be quantized. So how do you quantize it? So he basically interpreted this phi, okay, or even psi as the density, okay. He called it the density of the particle, okay, the density of the particle. And what density is it? If you take the mass of the particle, okay, as m, let us say there is one particle with mass m, then this mu times mod phi n squared or mod phi squared or different n's has to now be related to the density of the particle, okay, has now be related to the density of the particle, and the integral of this overall volume in one dimension overall length should give you mass. Okay. So mod phi squared is the density, not phi itself, but mod phi squared. He interpreted it as the density and he applied, okay, he quantized this wave by, I think this part we will take up in the next class because it's important to understand how you quantize the de Broglie wave. And in the next class, we will take up this problem, see what problems and issues exist with this description, and then go into how Schrodinger, by tweaking the interpretation slightly, landed on the actual Schrodinger's equation, which looks very deceptively similar to de Broglie's equation, but is completely different. Okay, so that will be the topic for Wednesday's class, and we may have a class. Hello, you have a question?
Sir, would you please look up that equation that you wrote after de Broglie's wave equation? I think there is an h square missing in that equation. Slightly up
Uh,
before this. Yeah, in this equation. It should be, I think, h
uh,
square by 2m.
oh yeah, 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 yeah. Oh yes, 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 yes. You are right. You are right. You are right. Yes. Yeah, yeah, yeah. Exactly. IH cross del psi by del t, and I have. Oh, yeah, yeah, yeah. You're right. I think that will do it. Yeah. So there is an, yeah, naturally, you need to have that. Yeah, because these are in the denominator, right? So these go into the numerator here, and you multiply it by h cross on both sides, you get, yeah, that's fine. Yeah, you get, this is v by h. Yeah, you're right. Okay, any other points? So that equation that I wrote, it has an h cross squared missing, and with the h cross supplied, it looks very much. So this is basically Schrodinger's equation, as you will see later. What is different between de Broglie's equation and Schrodinger's equation is how you interpret this psi. And of course, I'm not saying that Schrodinger basically took de Broglie's result and just changed the interpretation. No, that's not what he did. In de Broglie's result, he saw the key to solving the problems that de Broglie was facing. And we will see what problems de Broglie had when he employed this equation for particle dynamics. Yeah. All right. So we will conclude here. Don't worry about that little notes that went missing, because I uploaded this whole birth of quantum mechanics lecture notes that has everything, all of this, including all the derivations. So you don't need any other, you don't need to refer to my board work, which is probably much messier than that lecture notes. All right. So in next class on Wednesday, we will take up the issues with de Broglie's equation and how do you handle quantization in terms of particles. How does de Broglie's equation describe particles, and what additional things do we need to do, and what are the issues, what are the successes and failures of de Broglie's equation, and from there we will head into Schrodinger. We will probably have a class on this coming Friday so that we can complete Schrodinger this week, and from next week we can look at some applications of quantum mechanics, and probably you know, then we will move into relativity after that. Okay, so see you guys on Wednesday.
Thank you, sir.